Okay, so I guess we can start. Okay, thanks for the introduction, Yan Chao, and also thanks for joining me today. So I'm very excited to have this online visit and give a talk on some recent research work in my group on this machine autonomy. So most of my previous work is more on the perception part, building the visual scene understanding, database and train neural network to recognize what's going on inside the environment. In recent 2 years, so our group have been doing many work on this embodied AI with more application to autonomous driving. So today I would like to share with you some of our work to improving the generalization of the embodied AI. Okay, so I would like to motivate my talk with this very interesting video. So I will play you a video. So in this video, there is a kid and also there is a dog. So there are something happening here. So let's see this video first. So from this video, so there are a lot of interesting things happened, right? So at the beginning, so we see this kid observe that the dog is biting paper. Also, it looks very tasty, right? So then the kids took the action and go in there and grasp this paper and took this paper and test by himself. So this kind of trial and error. So he also gets feedback from the environment, right? So the test seems not that pleasant. So we human actually learn in the real world by interacting with the environment. So by acting on the observation and the perception we received, then we will take action and receive feedback. So this kind of embodied AI is a recent hot research topic in this field. So people are building a lot of such embodied AI with application to robotics, right, in the real world, such as autonomous driving, indoor navigation, and also so this robot dog for terrain navigation. So for this kind of embodied AI, traditionally people will use this kind of modular pipeline, right? So we have different modules such as perception, decision, planning and control module. Then observation will input, then perception module will doing this kind of object detection or segmentations and will be processed by this downstream modules and output action. Because of the popularity of neural network, people start thinking about using some neural network to replace the whole pipeline. Then we have this kind of neural decision making things. So this neural network will receive the observation, then we're doing all the process, then finally it will output the action. Sometimes people are not so happy about this kind of neural network for everything, then they just replace certain modules with neural network. Then we have this neural modular pipeline. So certain module is replaces by the neural network. So ideally, we want this pipeline to be optimized end-to-end. So if we link this pipeline with environment, then the whole framework then will become more like sequential decision making. So it's more like a framework of reinforcement learning, right? So this agent parameterized by some neural network will receive observation and feedback from the environment. Then it will output the action. So the action will fit into the environment and will proceed. So one issue when we use neural network as a model for the agent is that the neural network are prone to overfitting. So it will lead to very poor generalization ability of the agent. So if we change the environments, such as if we have another environment, unseen environment A, unseen environment B, and unseen environment C, so it's very difficult for the agent to generalize to the unseen environment. So that is a problem for that. So in this talk, I will summarize our work into three pillars. So here I summarize the work in three pillars that how can we improve the generalization of the embodied AI. So the first pillar I will talk about is on the data side. So it's on the environment side. So I think it's very important to build a diverse environment. Then we will also want to improve the diversity of the environment. The second pillar I will talk about towards generalizable AI is about the representation, right? For the agent's representation, so how can we learn generalizable representation? So I think that is representation learning is an overlooked topic in this reinforcement learning field, because usually people just use 2 or 3 multi-layer perceptions as parameters. But here I will show you that it's very important to have a good representation. The third part I will talk about is about the whole learning pipeline, right? So from the interaction between the agent and the environment. So how can we design a safe and efficient learning pipeline? Okay, so because we have relatively small group, so feel free to stop me and ask any questions you may have. Okay, so let's move into the first pillar, the data. So how can we improve the diversity of the environment? So the diversity of the environment is a long-standing problem in reinforcement learning, because a lot of the existing simulation environments, such as Atari or Mojoko environments, they have a fixed environment. You know, people also just train and test on the same environment. So from the perspective of computer vision researcher, so I'm not so sure why people can train and test on the same environment, but usually people do that. So that will lead to very poor generalization ability for the agent. So it cannot generalize to new environments. With the application to this self-driving, autonomous driving, so people build some simulators. Now, some existing simulators, such as CARLA and highway environments, they also have limited number of town maps and assets. So for CARLA environment, people usually like train on town 1 and evaluate the model on town 2, but still have very limited assets. So it's very easy for the agent to overfit the environment. So to address this issue towards more generalizable research on reinforcement learning and the imitation learning. So along with my student Chuan Yi and Zheng Hao, so we built a new driving simulator called MetaDrive. So one very key design for MetaDrive is that we have an open scenario design. So basically we want to keep the traffic scenario open, so we can either generate new traffic scenarios using some models, or we can input more real data from the driving data sets, such as Argoverse or Waymo open data sets, into the simulation environment, and then we can replace the scenario. Also, we have done a trade-off between the visual rendering and the efficiency and the flexibility. Because we are a research lab, so it's really hard for us to compete with NVIDIA or those self-driving companies. So we build this simulation environment for our own research on this reinforcement learning and imitation learning. This is also why I highlight this research, because this simulator is aimed for the research prototype. So based on this MetaDrive, we also built multiple reinforcement learning tasks and the benchmarks, such as safe expression, multi-agent IO, and more. So right now we open source this simulator through this link. So in the simulators, we have very toy visual observation. So, but we have very efficient simulation of the traffic scenarios. So that's why we have this trade-off. So based on this MetaDrive, we can generate a lot of new environments following some generation process. So here is an illustration of the procedural generation of the new environments. So in this simulation environment, we built many elementary traffic assets. So each asset will have some configurations, like we can see what is the weight of the lane and how many lanes we want. And then we can easily set those parameters. Then we further develop some algorithm, some search-based algorithm that can randomly sample from the predefined traffic assets. Then it's more like playing some Lego blocks. Then we can glue them together and turn them into a road network. Then each road network can be further turned into this interactive environment where we can train or test our agents. So this video showing you this sampling process. After we generate the road network, then we can turn this into an interactive environment. Then we can play this vehicle inside and run some tasks. Because of this procedure generation, now we can evaluate the generalization of the reinforcement learning algorithm. So here we just take some standard reinforcement learning algorithm, let's say PPO. Then because this procedure generation, we can generate the infinite number of interactive environments. So we split them into training and testing. So the plot on the right showing you the generalization performance. The horizontal axis is the number of training maps. The vertical axis is the performance on the train set and the test set. So you can see when we have a small number of training maps, there is a huge gap between the performance on the train sets and the on-scene test set. But as we include more training maps, then the generalization performance of the agent is greatly improved. Any questions for this part?
I was wondering, the other traffic that you showed in there, is that produced procedurally as well, or is there like a learned traffic model, or how is the traffic controlled outside of the ego vehicle?
Yeah, that's a great question. So for the surrounding traffic vehicles, they just actuated by some rule-based policies. So later I will show you some work that we try to use some learning-based algorithm for this traffic population. But for this, we just use some rule-based to control it. So here, this kind of generalization, you can see more about the generalization towards road structures instead of the traffic diversity.
I see. Okay, and the task here for generalization is just avoiding collisions, or what exactly is the RL trying
It's
to
more like to reach the destination and also avoid this collision. Just a percentage reach the final destinations. But it's a run out of land, then we will kill this. It's more considered as a failure case.
I see.
Okay. So
are you going to show also to predict the ranking function on the new roadmaps so that you could tell which ones might benefit the network the most without actually trying them?
Yeah, that's a good question. So for our data generator, we just randomly generate like 1,000. But we can dive into this and analyze like for which kind of maps that there are more problems or accidents. So that will be interesting directions. We also can make this map generator coupled with the agent. Maybe we can generate more corner cases based on the feedback of the agent. But right now, we just keep everything independent. So we can have another loop here on this. Okay, so here, let's continue on.
I just had a quick question also. Getting generalization within the same simulator doesn't seem too surprising, especially if the maps are generated with these building blocks, like you said. Like, how do you know you're not just generating your test maps after you generate 1,000 training maps?
Yeah, it's, so we use some retrieval-based method to check that. But I agree with you. So it's hard to check if they are very similar to each other, or how to measure the similarity between the environments. So we may have better metric to measure that. So we can measure that, and we can more intentionally generate a more diverse environment.
Are you also
randomly generate like 10 blocks and randomly generate the maps? Yeah.
Yeah, that makes sense.
So here are the evaluation on the head-out test environment. So you can see this Eagle car can reach the destination, but the driving behavior is very conservative. You know, this agent is more like just staying in the same lane because it's the safest way to reach the destination. So how can we encourage the diversity of the driving behaviors is still a standing problem. So from our experience of building simulator, we found out it's very difficult to define the reward function, right? So because it's a reinforcement learning environment. So how can we define a reward function to incentivize the agent? So it's still a problem. There could be some space for this inverse IO, like we can learn this reward function from human data. But still, it's hard to embed all our expectations into this single reward function. Okay, so based on this meta drive, we also can build other environments. So here is a safe reinforcement learning environment we built. You know, the safety is an issue for reinforcement learning. So people study this safe reinforcement learning. So it's basically this problem turn into a constraint optimization problem. So while we want to maximize the reward function, we also want to minimize this cost function. So we want the cost function within some threshold. So we evaluate many safe IO methods. So here is a demo video showing you the difference between this naive PPO agent and the agent trained from this constraint SAC agent. So there is a cost here. You can see here without any constraint, then this PPO agent will do all kinds of crazy stuff like scratch other cars and running into the traffic cones. So lead to a high cost. So that is also a very interesting problem. And based on meta driving, we also can study this multi-agent traffic simulation problem. So here I show you some environments we built on top of meta drive. So those environments are more like a multi-agent environments. So there are many a population of vehicles inside. So each vehicle is controlled by an independent policy. So in order to achieve this task, those vehicles have to coordinate with each other to pass this roundabout, toll gate, or this parking scenarios. So based on those environments, we developed some multi-agent reinforcement learning algorithm. So here is a paper we published last year on Europe's. So it's called coordinated policy optimization. For this multi-agent IO, we have two levels of coordination. So one is a local coordination, which emphasizes a neighborhood like Eagle car and its neighbors. They have to coordinate with its neighbors. Also, there is a local coordination factor. This factor is actually end-to-end optimized from the environment. So we found out under different multi-agent environments, this local coordination factor have different numbers, which means that different environment have different level of local coordination. We also have this global coordination. It's just the summation of all the individual rewards. And then we evaluate our method and compare with some other multi-agent IO. More interesting, there are some emergent behaviors from this training. So here I show you two videos. So we observed that some emergent cooperation behaviors. Some agents actually learn to yield to other vehicles because in some vehicle run into other vehicles. So both of vehicles will suffer from some collision, some cost. So then they learn to cooperate with each other. We also have this competition behavior. You see this green car, have this cutting for this drivings. So there are a lot of such interesting emergent social behaviors from this kind of coordination training. So previously I talked about procedural generation.
Does the cooperation and competition also happen when the other agents aren't following this coordinated policy?
Yes. So yeah, from the same trainings. So there is both cooperation and competitions.
Oh, but I mean,
more like so this environment, like this driving environment, is more like a mixed initiative environment. So sometimes in this classical AI, people study this fully cooperative environment, like each agent have to cooperate with each other to achieve the goal. So it's something between the two, like between the cooperation and the competition. You know, you don't want like run into other vehicles. You want to fully utilize every space. So that's why this problem is interesting for this multi-agent traffic.
great, thank you.
Do you think like the cooperation might result in unrealistic traffic behavior because they're, I don't know, maybe teaming up a little too much that it's not possible to happen in the real world?
Yeah, that's a good question. So I think right now the phenomenon we observe still remain pretty in nature. But I think there may be some cooperation like too severe, like it's not so nature in real world.
It could be interesting to modify this global reward with some term to make it look, you know, based on data, some data-driven term that says look like a motion pattern you've seen in like the new scenes data set or something like that. Something to make it more realistic, but also follow these local rewards.
Yeah, indeed. So yeah, I think that's a kind of hyper learning. Like right now, we just purely train from reinforcement learning, so there is no human priors here. But I think if we can incorporate some human driving data, then it will be more human-like. Okay, so then we move on. So then besides this procedure generation, we also have this data inputting, right? So we want to input the traffic scenarios from the real world. So here I call it a real to scene. You know, scene to real is more like you train some agent in simulation, then you want to deploy in the real world. And real to scene is the other way around. It's more like we borrow the assets or traffic scenarios from the real world and then enrich the diversity of the environment. So here I show you some HD maps inputted from the Waymo dataset or Argoverse dataset. We also can input scenarios from this driving datasets. They can further turn into this interactive environment. So here are more traffic scenarios imported from the Waymo dataset. So there are a lot of diversity there. So besides just simply importing, we have some recent works that try to also learn from this imported traffic scenario, and learn some generative model. You know, recently we have the diffusion model or the DALI 2 that can generate realistic samples. So here we also want to generate realistic scenarios. So we developed some deep generative model called the traffic gen that can first recursively generate a place the vehicles. So here showing you this recursive vehicle generation process. So after we generate the vehicles, we also generate its future trajectories. It will be long trajectories. Then we can then plug in those traffic scenarios in the simulation engines. So this demo video is showing you this generation process, and we can further generated traffic scenarios into the simulation. Now we can train our ego cars. So here are more results. So we have more synthesized results. So for each traffic scenario, you will notice there are some colors. Those color it actually indicates a traffic lights. So we also model the green light and the red light states in the traffic, because that control the overall traffic flows. So based on the synthesized results, we also show how the result can be used to improve the real world generalization. So here is the experiment. So we first evaluate how well the procedurally generated data, the agent trained on the procedurally generated data can work on the real data, because here we have a training set and a test set, both are real data. So if we just train on real data and test on real data, then we have the first column, 60%. So if we train this agent only on the procedurally generated data, then the result is very bad on the test set. There are more than 50% performance drop, which means the generalization the agent obtained from the procedurally generated data is not that good to the real world, because there's clearly a difference between this procedure generated data and the real world data. So if we train this agent on the synthetic data, on the data sample from our generative model, then we can recover such performance. So it even can improve the performance a little bit only on the agent trained on the real data, because we only have limited number of real data. So for the synthetic data, basically we can generate a huge number of such data and train our agents. There another result is that because we have this generative model, then we can intentionally manipulate this generative model and sample more corner cases, like more sample from the scenarios from this no probability regions. Then we can do some augmentation. So with this kind of augmentation, we can further decrease the safety violation for the agent. So that is that's showing you the power of this generative model. So with this synthetic environment and the generated data, we can improve the generalization, real world generalization of the agent. So any questions here?
I've got a quick question. So here, I think this synthetic data contains like more variations in the structures of the maps, and so that I can generalize better to the real data. So could you remind again what other variations are important compared to the procedurally generated data, so that the learned policy can generalize?
I see. Yeah. So one is road structures. Those road structure. So it's really difficult for the procedure generators to generate this real world like intersections and also this radiance of this turning. And also it's about neighborhoods. It's about the traffic flows. Right now, this traffic flow, all the vehicles are generated by this data-driven model. This is not like rule-based model. So that will also improve the generalization of the agent. Yeah.
I see.
I think that's two most important factors. There are many other factors because these are real data, then they have better real world behaviors, driving behaviors, I guess.
Yeah. Cool.
So the map itself is generated here. You're not using Waymo to seed the map.
Oh, the map is still the same. So the map is a predefined HD map. So the model, so our generative model will take the HD map and generate traffic views.
Oh, okay.
Okay, so that's this first part. Then improving the diversity of the environment. Then we move into the second part, into the how can we learn a generalizable representation? Because I guess most of you are graphics people, so for the representation learning, probably I can go faster due to the time limit. So for the representation, we have this neural network. For reinforcement learning, people usually give like 2 or 3 layers representations, the 2 or 3 layers multi-perception as a representation. So it's not that good. Also for the training environment, it's very synthetic. So if we want to improve the real world generalization, we want to train this policy on the real world directly. So, but that is impossible. We can do this kind of feedback training. We still want to pre-train this policy representation with the real world data. So the issue is how can we get driving data, right? So because we are research lab, so we don't have this data collection vehicles. So what we are looking into is YouTube. YouTube have a lot of videos. Also, they have a lot of driving videos. So here I show you one YouTube channel. So there are some YouTuber called Jayuta. So this guy upload a lot of driving videos to his channel. So you can see there are a lot of different driving videos, like driving in downtown New York, driving in Miami, driving in Paris, driving in Morocco. So it's driving all over the world. I guess this guy just flows to some place and put some cameras on the dashboard. Even more surprisingly, there are so many views for each video. You can see here for this driving in this boring downtown New York, there are more than 8 million views. So I guess some people just sitting at home and watching those videos. So here I show you some of the videos we downloaded from that channel. So you can see those driving video contains a lot of diversity, like the weather, different weather conditions, also the day and the night, the rural scenes and urban scenes. So they provide a great source to learn the representations. So right now, then we want to learn some representations using this real-world driving data. So along with my student Shihang, so we have a recent ECCV paper. So we call it learning to drive by watching YouTube video. So you can watch enough YouTube videos, then you can learn how to drive. Right. So we want to develop some self-supervised learning algorithm on this real-world driving data. So speaking of self-supervised learning, one very popular method is this contrastive learning. Right? So contrast learning, we can like naively apply it here. So it's more like giving some video frames. So we want to create this positive pair. So we just doing some augmentation on the sampled frames. Then we can create a positive pair. For the negative pairs, we can then sample from some random frames from another driving video, right? So we can create this positive pair and negative pairs. Then we can train this contrastive learning. But one issue with this kind of design is that the learning feature may not be effective for decision making, right? Because here we are talking about this policy pre-training for this downstream decision making task, rather than learn some visual representation for visual recognition. So if we just do this feature learning naively, then this feature will carry a lot of redundant useless information about such as the skies or the trees, which is not so relevant to the downstream driving task. So then we found out the human action is actually very important to generate those driving video. Here, if the human is turning left, then the whole driving video will turn left. So going straight, then the whole video will go in straight. So here are some of the videos under different driving actions. We have this straight driving scenes. We also have this right turning scenes. So those are different videos. They share the similarities conditional on the driving actions. So that make us think, how can we design this policy pre-training with human action inside? So we want to put a human action inside, but for the driving video we downloaded, we don't have the human driving data. So what we use is using some auto-labeling methods. So we first train some inverse dynamics prediction model from some label data set, the Waymo data set or Argoverse data set. They have this driving driver behavior data collected. So we just train some this inverse dynamics model to predict the action happen between 2 frames, right? So here we use the OptiFlow as a feature for the inverse dynamics model, because that will make the training the model less dependent on the driving contents. So then we just apply the training model on our YouTube video on their OptiFlow of the video frames. Then we can associate pseudo labels for each one of the video frame. Because this prediction task is relatively easy, we just do the 3 classes, like turning left, turning right, and go straight. Then we can have a relatively good accuracy. So I think the accuracy is about 80%. Then we use this pseudo label with a massive number of video frame and train our model. So in this case, then it will become action condition contrastive learning. So for some right turn scenes, we can create a positive frame by sampling a video frame from another right turn scenes, right? So then they share the similarity, they both turning right. And for the negative pair, then we can sample from some straight drive scene and the left driving scenes. So in that case, we can create this contrastive pairs and train with this contrastive learning. So from this kind of design, the action is naturally modeled inside this pair construction, then we can lead to the feature that's the most relevant to the decision making and the action for the driving. So after this kind of training, so then we evaluate the pre-trained weight and compare with the other self-supervised method and even some ImageNet pre-trained weight on some driving tasks. So we evaluate the weight on this CARLA data sets for some imitation learning tasks. So here it is on the imitation learning task. So the CARLA data set provides some human demonstration. So we evaluate the under different data percentage, like 10% demonstration, 20% demonstration, 40% demonstration. So how much the representations can help the final performance. So you can see here for our method, the HACO, so this representation can achieve better performance than the other self-supervised methods such as MoCo, and also it outperforms the ImageNet pre-trained weight under different demonstrations. That is interesting because if you think about that, for ImageNet, they only contain this dog or cat, so they shouldn't be that useful for this driving task. Right? So if we can pre-train the data on the driving data we have, then we can improve the performance.
Bolay, what are you predicting here? What are these numbers exactly measuring?
The number is more like predicting their imitation. So after we train with imitation learning, so how this agent can reach the destinations. So it's a more like a navigation task. So we are doing imitation learning. So if this agent can reach some destination, then consider as correct. So here is a successful case. And so after this imitation learning trainings, then this vehicle can drive in the environment. So right now the observation is the RGB input.
Are we looking at the roughly what the model sees in that overhead view?
No, it's a first round view, because right now we want to evaluate if you just input the first view like RGB frames, how well it performs. So in the next experiment, I will show you that. So for this reinforcement learning, so for this one, this experiment is interesting because previously people cannot make the reinforcement learning work with this first view observation. People usually train this top-down view mask. Then we can train with this reinforcement learning. So here, this experiment shows that with proper feature extractor, we can actually fit the RGB observations to train this reinforcement learning tasks. So this result showing you the performance. So the horizontal axis is training samples for this reinforcement learning. Vertical axis is the performance. So as you can see, you just use ImageNet or random initialization. So it doesn't work at all. This reinforcement learning, if you train longer, then it doesn't work. But with the proper initialization, it can actually work. So that is showing you the power of the representations. We can have a good representation trained for this driving environment, then can have better generalization, have higher sample efficiency.
So MoCo here is these contrastive learning on the YouTube videos, right?
Mm-hmm.
Not on email. Okay.
Yeah, we just train on this YouTube video and directly apply the training model in the CARLA environment. So CARLA have relatively realistic observations.
I see. Cool.
Yeah, so we can improve over the previous self-supervised learning method and also this pre-trained ImageNet weight. Okay, so that's the second part. So pre-training on real-world data. Then we move into the third part, one of my favorite parts, learning pipeline. So how can we design a safe and efficient learning pipeline? So one issue with reinforcement learning is that there is no safety guarantees. So the video on the right, I'm showing you this agent in the learning process, right? So because this reinforcement learning is a trial and error exploration, then this agent have to make a lot of mistakes, like scratching on the car, running into traffic cone, causing a lot of accidents before it can pick up the right driving behaviors. So that is a tolerance. We want to apply this method in the real world, right? So then we want to improve the safety of the exploration. So how can we improve that? So here we borrow some ideas from how we human learn to drive in the real world, right? Yeah, so when we start learning to drive, we will first take some paper test, then we will get our learner's permits. Then we can directly drive the vehicle, but under the guidance of an expert. So this kind of guided learning should be the paradigm for this kind of decision making. So we want to model this guided learning for our training. Then we explore this human in the loop reinforcement learning. So instead of the interaction between the agent and the environment, then we include the experts, the human as an expert inside this learning loop. Now there are two roles for the human expert. The first is to safeguard the active exploration of the learner. The second is to demonstrate the correct action when needed, right? So here, I should remind you that we keep a reinforcement learning, which means this agent still have a degree of freedom for exploration. It only, the human only intervene when needed. When needed means this agent run into some dangerous situation, then the agent will intervene in the process. Otherwise, we will just leave this agent alone to explore this environment. So that is our setting. So humans want to just monitor this exploration. They only help the agent when needed. Then we have, based on this kind of modeling, so we have a recent work published at the ICOR. So we developed some method to address the technical challenge here. So the technical challenge here is the training data right now we have become more like mixed data, mixed trajectory. So mixed trajectory means the first half of the data is generated by the learner because the learner is exploring the environment. So at some point, there are some intervention happening. Then all the yellow trajectories will be human demonstration. So if you have some knowledge on reinforcement learning, so you will know right now the problem become off policy learning. Right? So because the data is out of the original learner's distribution, so we have to address this. Then we develop some learning algorithm called HACO, so Human AI Copilot optimization. So we borrow some concept from this offline reinforcement learning developed by group Sergey Levin. So they study that they have some method called conservative Q learning for offline IO. So we use Q learning here, conservative Q learning here. So we want this agent to be pessimistic to agent's action and to be optimistic about expert action. We also devise some intervention minimization cost Q function here because we want to minimize the intervention from human over time. Otherwise, this agent will just exploit the humans. So we want that as the training goes on, there are less and less intervention from the human. So combine the two, then we have this kind of policy optimization to maximize this Q function and also minimize this cost Q function. So that a little bit technical. So if you want to know the details, so you can refer back to the paper. So here I would like to show you a demo video. So this demo video showing you the whole process of learning to drive in the CARLA environment. So you can see at the beginning, there is the training time. So at the beginning, this agent don't know how to drive the vehicle, then it's a purely human demonstration. Human just demonstrate how to drive inside the environment. Then we have this human experts to do the demonstration. After some time, after like 6 minutes, so this agent, you can see already learn how to drive in the straight road, right? So it can drive in straightly, but you can see there is a corner coming. So this agent still don't know how to turn around the corner. Then there's some intervention from human. So here we continue the demonstration. Whenever the agent don't know how to do it, then there's some intervention. So after about 10 minutes of training, so this agent already learn how to drive freely inside this environment. So you can see here is a demo video without any intervention from the humans. So after only like 10 minutes of this interactive learning. So I should see here, the observation right now is just the top-down observation. So it's not the RGB observation. The RGB observation is just too slow to learn. So we just use top-down ground truth as input for the agent. Okay, so any questions here? Okay, so let's continue. Then besides, so recently I'm very excited about this kind of human in the loop machine learning. So in the previous work, it's more about human in the loop learning. It's more like in training. We have human in the process. Then in testing, this agent will just act on its own. But have you thought about human in the loop inference, right? So human in the loop inference is more like in the testing time, human and collaborate with AI or the robot to achieve the goal. So this kind of human in the inference is actually very popular for this human machine teaming application or this shared control application, such as human can collaborate with some robot arm to accomplish this sampling task, or we have this variable robot as a skeleton. Like they can collaborate with the robot to achieve the task, and we also can use the robot to empower human, right? So we have some ongoing works that explore this human AI shared control. So here I show you an agent. So this agent just trained with reinforcement learning in this Mojuko environment. So after training, this agent can only do this moving task. But there are some fundamental questions remain here. So one is how can we control the trained agent? Another one is what have been learned inside the agent. So if you know my previous work, so we continue doing this AI interpretability. So we try to understand what have been learned inside this AI model. So right now we want to understand those decision-making agents. So why they make some decision makings, right? So to better understand that, we developed some method called policy dissection to analyze their internal representation of the learned agents. So what we are doing is that we first do some policy rollout, then we can collect a lot of observation for the kinematics observation of the agents. At the same time, we also can collect a lot of neural activations for the agent. Then we can develop some time series analysis method and match the frequency between the two. Then we can associate the internal representation with certain kinematic attributes, right? So after we have this annotation for their internals, then we can activate or deactivate certain neural regions. Then we can evoke certain behaviors from the agent. So you can think about this more like a neuroscience, right? So we have this mice, then we want to study their behaviors. We will activate a certain brain regions, then we will evoke certain behaviors. So here is a demo video showing you that for this agent, training agents, we can, after we apply our methods, then human can press some keys, then we can evoke certain behavior from the agent. Like we want this agent move left, then we can press a key and activate certain regions, then this agent can move left. So it's more like we can command the agent to move around inside the environment, make this agent more controllable to human orders. Now it's going to stop or spinning around, then the agent will just spinning around. So here's another environment we apply. So we apply our method to this lagged robots. You know, this lagged robots is just this training environment, just walking in front. We train this agent with PPO. But if we change the testing environment by like including some obstacles, then this training agent cannot accomplish this goal. But we can combine this agent with humans. Right now, then we can navigate this agent inside this new environment, like there are some obstacles. Then right now the agent can press some keys. then we can activate certain behavior of the agent, such as the turning left and the turning right. Okay, Leo, bye-bye. So we can evoke certain behavior from the agent. The agent can stop and turning left and turning right. Then we can achieve these tasks. So that is a kind of hyper control, like a human AI shared control. Like a human is more like issue high-level orders. Then this agent will execute the low-level control signals. So here's another. So we further quantify this, right? So we call it test time generalization through the shared control, because I already showing you that if this agent trained in this training environment, if we deploy this agent in some testing environment full of obstacles, then the reward is very low. But if we can have this human plus agent in the new environment, then we can recover this performance. You can achieve the similar performance for the agent, like directly trained in the new environment. So we achieve this kind of test time generalization by just combining human with agent. Here are more results that we apply our method to some Cassie robot in the Isaka gym environment. So this Cassie is a bipedal robot. So trained with reinforcement learning, just walking in front. So we can apply our method to this training agent. Then we can discover a lot of skills or the primitives behaviors inside this, such as crunch, even some backflip actions can be discovered. Then we can combine those skills in this parkour environment. Right now, this is a hybrid control environment, like a human can press a certain key, then we can control the behavior of this agent, moving right and moving forward. Then there is a barrier there, then we can press some keys to let this agent to jump over the barrier. And then there is a bar there, then we can ask the agent to crunch, then it can pass this complex environment. So, so I think this kind of human AI shared control will be very interesting for this future human machine or human robot collaborations. Okay, so I would like to
well, can I ask a quick question?
Yeah, sure.
Yes, like the previous work is very, very interesting. And I was thinking, especially in the context of, say, autonomous driving, currently it's human in the loop, right? But like after this interpretability analysis, can like this kind of end-to-end RL policy be combined with some kind of rule-based policy to, like, because currently I feel like most autonomous driving companies are using rule-based controllers instead of any kind of learned controllers. Yeah, so just wondering what's your thought on that.
Yeah, that's a good question. So one thing for the driving scenario is that they already have this interface, the human machine interface, just as driving wheels and this pedals for acceleration, right? So they already help you walk up everything on that. But I think there's still some space that we can have more like hierarchical design. For this training agents, we can interpret that. Then we have some primitives. Then the rule-based will just build on top of the primitives. Then we can achieve faster learnings, because usually it's more like a hierarchical IO, right? Just have another level of hierarchies. I think that can greatly improve the sample efficiency and also maybe safety of that. Yeah,
I was thinking like now on second thought, this interpretability is kind of in the control aspect, right? Like which part of the policy is controlling which part of the morphology. Have you done any like work on interpretability with respect to the observation? So like which parts or like at a behavior level, well, maybe the observation level, like the policy is looking at this something so that it's driving this direction. So this kind of interpretability analysis.
Yeah, that's a kind of interpretability is still much less explored. I think some previous people explore this like using some like a gradient cam or backpropagation to generate heat map to highlight that. I think that is interesting, but still there's still a long way to go. Whether there are only some correlation, whether there are some causality relations. I think there still need to some future work on this. Also for some accident, like autonomous driving, some accident happen, some people get killed, then we want to do this accountability, right? So whose responsibility is that? So which module is going wrong? So that will, I think it's a future direction for this. It's about AI safety and AI ethics, I think.
Thank you. Yeah, exactly. Like, you know, safety. I mean, applying RL in the safety critical scenario, we definitely needs like interpretability and yeah.
Yeah.
Thanks for the answers. Yeah.
Okay, so to summarize, so in this talk, so I talk about 3 pillars towards generalizable AI. So for the data, so we want to improve the diversity of the environments. For the representation, so we want to have a more generalizable representations. We want to pre-train on real data. And also for the learning pipeline, we want to involve human in this process for learning, for both learning and inference. Okay, so I would like to stop here. So yeah, so I'm building a new lab at the UCLA, so I'm open to research collaborations. I'm also looking for talented PhD students. Okay, so any questions or suggestions? Thank you.